Hello, good morning, good evening, good afternoon, everybody. It is my great pleasure to welcome my friend and colleague from Odense, University of Southern Denmark, Jens KAAD, and he will tell us about spectral localizers in KK theory. Jens, it's all yours. Take it away.
Thanks a lot. Thanks a lot, Piotr, for inviting me to speak in the North Atlantic Noncommutative Geometry seminar. It's a pleasure for me to speak on this occasion. The topic of my talk today is, as it says in the title, spectral localizers in KK theory. And I will say immediately that my work is complementary to work of Bram Meslin and his PhD student, Yuejiao Li, because we are focusing on the even case and they're focusing on the odd case. So today I'm talking about the even case. So I'm going to start out by just talking about spectral localizers as they were introduced by these two people. Let me see. Terry Loring and Hermann Schulz-Balves. So they introduced spectral localizers as a tool to compute the index pairing between K-theory and K-homology. And this has been very successful, what they have been doing with actually lots of applications, both in mathematical physics, but also in theoretical physics. And one of the reasons why this approach is working very well is that it allows you to implement index computations on a computer. So you can use numerical methods to compute indices.
ChatGPT.
What?
ChatGPT.
I didn't understand that.
You can use ChatGPT.
Yeah, you can do that perhaps. So this is due to these two people in a series of papers, and I'm not going to tell you what their result looks like in the even case. So there's a similar result available for the odd case, but this talk is really about the even case. So let's see. Here's first some context. So here you have a projection which acts on a separable Hilbert space, and you have a closed unbounded operator acting on the same Hilbert space. And these two, or these objects, they have to satisfy some conditions. First of all, you boost your closed unbounded operator so that it becomes a self-adjoint unbounded operator. The way you do that is to form this 2 times 2 matrix where you put D naught and its adjoint on the anti-diagonal. This is then always self-adjoint. So you know that the spectrum of capital D here is contained in the real line. And in particular, once you add the imaginary unit, you get an invertible unbounded operator, and the inverse is a bounded operator acting on your Hilbert space. And here in the first condition, I'm saying that this inverse, capital D plus I inverse, is not just bounded, it has to be a compact operator on your Hilbert space. So this is said in a brief way by saying that capital D is compact resolvent. The second condition is linking D naught to the projection P. So the second condition says that the projection P should have a quantum derivative with respect to D naught. And this means that my projection is assumed to preserve the domain of d naught, and then this commutator between d naught and p makes sense on the domain of d naught, and I want this commutator to extend to a bounded operator on the Hilbert space, and this is then my quantum derivative of the projection p with respect to d naught. So once I have these two conditions satisfied, I have an index problem. So in this setting, I can compress d naught with my projection p, and I get a new closed unbounded operator acting on the image of the old domain under the projection p, and it takes values inside the Hilbert space, which is given just by the image of the projection. But this is not just a closed unbounded operator. Actually, this is an unbounded Fredholm operator. So it has a finite dimensional kernel and co-kernel. So I can make sense of the index of this unbounded Fredholm operator. It is just the dimension of the kernel minus the dimension of the co-kernel. And now a lot of effort has been spent on trying to compute this kind of index in various settings. And there's a vast literature available on this subject. To mention just two highlights, the Atiyah-Singer index theorem and the local index theorem in non-commutative geometry due to Alain Kohn and Henri Moscovici.
Jens, please allow me to ask a very dummy, embarrassing question. So I'm used to the definition of Fredholm operators when they are bounded. How exactly you define them when they are unbounded? Because I'm used to saying, okay, modulo compact, they are invertible. Do you have something
but
similar?
here I'm just saying that I have finite dimensional kernel and co-kernel.
Okay, so yeah, down to earth definition. Okay.
Yes, just that. Okay, so the spectral localizer approach by Terry Loring and Hermann Schulz-Baldes is a new approach to computing this index, or this index pairing, as you can interpret it. So
I'm sorry, can I ask a question?
Yeah, go ahead.
Yeah, I'm asking that this projection is a map from this Hilbert space.
Can you show yourself? Can you switch on your camera so that we see when you ask a question?
Yeah.
Okay,
Hello.
great.
Yeah, so I'm asking that this P is a projection operator from this Hilbert space H to which subspace? Are you talking about the domain of D0?
So P is just an operator on the Hilbert space H.
Yeah, it's a projection, right? So it will project to some subspace of H. So what kind of subspace
That's
you are
just what I
taking?
have right here. PH, that is the image of the projection.
Okay. So So any image. So okay, I see.
Yeah, it's just any bounded operator on the Hilbert space which is self-adjoint and squares to itself.
Okay.
Yeah.
Okay. Thanks a lot.
Okay, so now I can define this spectral localizer for you in this context. And what you do is that you fix a parameter rho, which is strictly positive, and then I form the corresponding spectral projection coming from capital D and this closed interval from minus rho to rho. And how to think about this? Well, because capital D has compact resolvent, you know that your Hilbert space has an orthonormal basis of eigenvectors, and also all the eigenspaces are finite dimensional. So what I do is that I look at the direct sum of all the eigenspaces where the eigenvalue belongs to this closed interval from minus rho to rho, and then I look at the corresponding projection onto this direct sum of eigenspaces. So that's what the spectral projection is in this case. And you see also immediately that it's actually a finite rank operator on this Hilbert space. And moreover, I'm here localizing in the spectrum of capital D, because this spectral projection, it really only depends on the part of the spectrum of capital D, which is contained in this closed interval from minus rho to rho. So this is what I mean when I say spectral localizer. It means that I'm localizing in the spectrum in this fashion. I only the part of the spectrum of D, which is contained in this closed interval from minus rho to rho. And here's now the definition of the spectral localizer. So here I take another parameter, kappa, which is also strictly greater than 0. And first of all, I look at this 2 times 2 matrix. So in here, I have capital D sitting on the anti-diagonal, but rescaled with kappa. And then afterwards, I have something on the diagonal also. On the diagonal, I see my projection P actually in the form of 2P minus 1 in the upper left corner. And then I have minus 2P minus 1 in the lower right corner. So what I have inside this 2 times 2 matrix is another self-adjoint unbounded operator. But then I compress it with the spectral projection Q rho from both sides. And in this fashion, I get a bounded self-adjoint operator acting on this finite dimensional Hilbert space, which is the image of my projection, my spectral projection Q rho. So that's the definition of the spectral localizer, and it only depends on the part of the spectrum of capital D, which belongs to this closed interval from minus rho to rho.
Excuse me, why does there appears here D0 and previously it was D?
I have formed capital D out of D0.
Yeah.
So capital D is just what I have on the anti-diagonal here.
Yeah.
That was how I started out.
Yeah.
Thank you.
And here's the main theorem of Terry Loring and Hermann Schulz-Baldes in the even case. So they are supposing that D naught is invertible. So 0 is not in the spectrum of D naught. So D naught has no index. And then they've been able to prove that once kappa is small enough and rho is large enough, and they are able to quantify what is meant by small enough and large enough. This is actually something very precise, but I'm not going into details right now about that matter. So once kappa is small enough and rho is large enough, they were able to prove that then the spectral localizer is actually an invertible operator on this finite dimensional Hilbert space. And since it is also self-adjoint, the spectral localizer then has a signature. So the signature, how do you find it? You look at all of the eigenspaces where the eigenvalue is strictly positive, and you sum up all of the dimensions. And then you look at all the eigenspaces where the eigenvalue is strictly negative, and you subtract all of these dimensions, then you get the signature. So here on the left-hand side, I have half the signature of this spectral localizer. And on the right-hand side, I have the index of my unbounded Fredholm operator.
Jens, allow me just a second, Adam. I have this very dummy question again. Is there any relationship between P, the projection P, and D0, or they are just married randomly at will, on a whim?
They are married randomly, except that they interact in this fashion so that P has a quantum derivative with respect to D naught.
Okay, I've got you. Okay, thanks. Adam, your turn.
Yes, if you could go back to this slide with this equality between this half of a signature and so Okay, without knowing this theorem, is it somehow visible that the signature would be always even number, since it follows, yes, from this index is always an integer, therefore the signature being the fact that the half of the signature is index means that the signature is always even, and I don't know whether it is somehow clear that for large rho and small kappa it would
Yeah,
be the case.
it's not something that is that you can see straight away.
Okay.
Actually, if D naught had a non-trivial index, then this theorem would be false as it stands.
Mhm. Okay, so this
Say
is in particular.
the signature need not be even.
Okay, thank you.
Yeah. Okay, so this is what could be called, so this is the spectral localizer approach to computing the even index pairing actually between K-theory and K-homology. It's possible to interpret it in this fashion. This talk is really about spectral localizers in KK theory. So this could have been called spectral localizers in K-homology. I want to talk about spectral localizers in KK theory. So now there are some brief reminders on KK theory so that we are on the same page. So here, what is KK theory? We have two separable C-star algebras in the game, A and B. And out of this, Kasparov realized how to construct a very interesting
Jens, hi, it's Ludwig. Hi.
Hi,
Jens,
Ludwig.
can you hear me?
Yeah, but we cannot see you.
Okay.
Now better.
So, Jens, so of course, okay, well, I know this a little bit, this Herman Loring paper. So, is there any reason to use the left-hand side to compute the index instead of the right-hand side? It's finite dimensional, perhaps, but is it easier to compute this pairing? Okay, that's in examples.
I think the answer is yes. And that is one of the reasons why I've been looking at it. So I'm not that familiar with all the applications of this result because I'm...
Yeah, you remember in one of the examples, they have some few dozens, I mean, less than 100 dimension of this space to get the index, but depends on the example probably. Okay. So.
It does.
Okay. Thanks.
Okay, so out of these separable C-star algebras, we have the bivariant K-theory or the KK theory for the pair A comma B. And here I'm focusing on the even case. So for us, there's only the even KK group. There's also an odd KK group, but it's not relevant for this talk. The elements in KK theory, they're all given by even bounded Kasparov modules. They are equivalence classes of even bounded Kasparov modules up to what could be called stable operator homotopy. It's not so important that you know the precise definitions for this talk. What I think you should be aware of is that typically if you have two separable C-star algebras, then it's not so difficult to construct examples of elements inside this KK group. So there are many, many examples of concrete, even bounded Kasparov modules. So you have many examples of elements in KK theory, typically. Now, what we should know is that if I look at two special cases, so if I look at the special case where the first entry, capital A, is the complex numbers, then the corresponding KK group is isomorphic to the K theory of the second entry. And another special case is when the second entry is the complex numbers, then the KK group is isomorphic to the analytic K-homology of the first entry. So both of these theories, K theory and k-homology, they are contained inside KK theory as special cases. What really makes KK theory interesting is the existence of the interior Kasparov product, which is a bilinear and associative pairing between KK groups. So if you have an element in the KK theory of A comma B and another one in the KK theory of B comma C, well, you can take their interior Kasparov product and get an element inside the KK theory of A comma C. So when you take the interior Kasparov product, the C star algebra in the middle here disappears. So also a lot of effort has been spent on computing this interior Kasparov product in various cases. One case which is interesting is when both A and C here are equal to the complex numbers. So in this case, so when both A and C are the complex numbers, then the interior Kasparov product actually takes values in the KK theory of the complex numbers, comma, the complex numbers. So it takes values in the K theory of the complex numbers, which is just a abelian group of integers. So in this case, the interior Kasparov product is integer valued, and what you have on the left-hand side, the first factor is just the K theory of B, and the second factor is isomorphic to the analytic K-homology of B. And this interior Kasparov product really recovers the well-known index pairing between K theory and K-homology. So the reason why, or one of the reasons why I am saying all this, is that you can now reinterpret the results of Terry Loring and Hermann Schulz-Baldes as a result about computing the interior Kasparov product in this particular case, where both the entry A here and the entry C, when they're both equal to the complex numbers. Because the result of Terry Loring and Hermann Schulz-Baldes is really about computing the index pairing in the even case. So this leads me to the main question of this talk. So let's see. So suppose now that I have a class in KK theory. So this class here is represented by some even bounded Kasparov module, and so I can take interior Kasparov products with this class. What I get out of this is a homomorphism from the K theory of A to the K theory of B. Because the K theory of A here is KK theory of complex numbers, comma A. And when I take the interior Kasparov product with this class, I get an element in the KK theory of the complex numbers, comma B, which is just the K theory of B. So out of this class in KK theory, I get a homomorphism between the K theory of A and the K theory of B. And this homomorphism is called the index homomorphism. And so it generalizes the index pairing between K theory and K-homology. And the main question is, well, can I actually compute this index homomorphism by using spectral localizers? And in this way, generalize the result of Loring and Schulz-Baldes regarding the index pairing. So that is the question I would like to answer in this talk. And the first problem that you encounter here, the first problem that you encounter immediately is that, well, okay, I have a class in KK theory given by a bounded Kasparov module, but when I look at the spectral localizer approach of Loring and Schulz-Baldes, I had some unbounded operators in the game. So the first thing you have to do is to get some unbounded operators into the picture. And this is entirely possible due to an old result of Saad Baj and Pierre Julck. This is a result dating back to 1983. So I'm not going to review that result of Baj and Julck.
Sorry, again, a stupid question. How do you specialize to get the case of Loring and Schultz and Baldes? What do you specialize to what?
That would be the case where the second C-star algebra B has the complex numbers.
Okay.
Because
okay, and then in integers. Okay. Mm-hmm.
Because it's really about computing the index pairing.
Yeah.
What they're doing. But we generalize by looking at this index homomorphism instead.
Okay.
Whether we can compute that one.
And then it will be index pairing between A and A, right?
Yeah, exactly.
Mm-hmm. Okay. Mm-hmm. Yeah, thank you.
Yes. So now I'm going to talk about unbounded Kasparov modules. So I'm going to review that because it plays a central role in this talk. So what is an unbounded Kasparov module? Again, I'm here focusing on the even case. So I look at even unbounded Kasparov modules. The setting is the same as before. I have two separable C-star algebras, A and B. Then we have a little bit of extra information. We also have a norm-dense star subalgebra of capital A. And typically this curly A here is referred to as the coordinate algebra of my unbounded Kasparov module. So I talk about an unbounded Kasparov module from the coordinate algebra with values inside capital B, which is a kind of coefficient C-star algebra. Okay, what is it? It consists of 3 ingredients. The first ingredient has a lot of information in it. The first ingredient is a Hilbert C-star module, capital X, over this C-star algebra, capital B. And if you don't know much about Hilbert C-star modules, then think about what would happen if you had a Hilbert space and you wanted to replace the complex numbers by a C-star algebra, capital B. And then you essentially arrive at the definition of a Hilbert C-star module straight away. So I have an inner product in this case with values in the C-star algebra, capital B. So capital B is now kind of coefficient C-star algebra. I have some more information here. I also have a left action of the C-star algebra, capital A. This left action is given by a star homomorphism defined on A with values in, well, not the bounded operators on my Hilbert C-star module, because unfortunately there are examples of bounded operators on Hilbert C-star modules which do not have an adjoint. So instead, I look at a star homomorphism with values in the bounded adjointable operators on my Hilbert C-star module. So that's the bounded operators which have an adjoint. And then, so what I've been saying so far can be summarized by just saying capital X is a C-star correspondence from capital A to capital B. And then there's an extra little technical detail. My Hilbert C-star module has to be countably generated. So that's the analog of being separable for Hilbert C-star modules. Second ingredient is a self-adjoint unbounded operator acting on this Hilbert C-star module. It's typically referred to as the abstract Dirac operator of my unbounded Kasparov module. So self-adjointness here means that capital D is equal to its own adjoint. In particular, the domain of capital D is the same thing as the domain of its adjoint. Third ingredient, that's a soft one. It's just a grading operator because I'm in the even case. So this grading operator is a self-adjoint unitary operator acting on my Hilbert star module. So it's self-adjoint and it squares to the unit. These three ingredients are linked together by 4 conditions. Okay, so let's see the conditions. They are here. So the first condition concerns the grading. So it says that the abstract Dirac operator is odd. So it anti-commutes with the grading operator. And then all the elements coming from the C star algebra A, they're all even. So they all commute with the grading operator gamma. The second condition concerns the self-adjoint unbounded operator D. And this is a condition that you do not really see if you were only working with Hilbert spaces. Because for Hilbert spaces, you're so lucky that the spectrum of a self-adjoint unbounded operator is automatically contained in the real line. That is not the case when you work with Hilbert C-star modules. So you have to put that as an extra condition on your abstract Dirac operator. Okay, so this can be boiled down to just requiring that once I either add or subtract the imaginary unit, I get a surjective unbounded operator. So this second condition says that my abstract Dirac operator is regular. So I'm looking at a self-adjoint and regular unbounded operator. But regularity is really just there to make sure that the spectrum of the abstract Dirac operator is contained in the real line. And you need that in order to have a well-functioning functional calculus for your abstract Dirac operator. A third condition concerns the interplay between the coordinate algebra and the abstract Dirac operator. It says that all of the elements coming from the coordinate algebra have a quantum derivative with respect to the abstract Dirac operator. So they're all going to preserve the domain of the abstract Dirac operator, and then this commutator makes sense on the domain, and I'm requiring that it extends to a bounded operator on the whole Hilbert C-star module. This bounded operator, I call it D of A, and it's then kind of the quantum derivative of my element A with respect to the abstract Dirac operator. Final condition. So now, because of condition 2, I know that when I add the imaginary unit to the abstract Dirac operator, I get an invertible unbounded operator, and the inverse is going to be a bounded operator on my Hilbert C-star module. In fact, it's bounded adjointable. The adjoint is given by the inverse of the abstract Dirac operator minus the imaginary unit. So this resolvent here is, because of condition 2, it's a bounded adjointable operator on my Hilbert C-star module. I'm requiring a bit more here. I want this adjointable operator to be compact. So it should act as a compact operator on my Hilbert C-star module. It's a compact operator in the sense of Hilbert C-star module theory, not in the sense of Banach space theory. Okay, this is any questions?
May I ask some questions?
Yes.
I have three questions, but hopefully they will be quick. First of all, this D and this L of X, those bounded adjointable operators are meant to be bilinear.
That's automatic once they are adjointable.
Okay, for the L of X, but also for D?
That's also automatic by self-adjointness.
Okay, second question, do you really want this D plus I to be strictly surjective or only having dense range?
If it has dense range, it's automatically surjective because D is closed.
Even if you defined it only on this domain of D, not necessarily on entire?
Yeah. So
Aha.
it's enough for checking 2 to check that that it has dense range.
Okay, okay. Thank you. And last questions. Do you assume that this curly A is closed under holomorphic calculus?
I do not need to assume that. If I wanted to, I could enlarge curly A and make it closed on calculus.
Okay. Okay, thank you.
Thanks a lot. Nice questions. Yeah. So, I mean, maybe I should point that out. I could, so this little d here, that actually gives you a derivation defined on curly A with values in the bounded adjoinable operators on capital X. And because capital D is closed, this derivation is going to be closable. So you can take the closure of that derivation, and the corresponding domain is going to be closed on the holomorphic functional calculus.
I
How I
see.
could enlarge my coordinate algebra if I wanted to.
Makes sense. Okay, thank you.
Okay, so in case you like spectral triples better than unbounded Kasparov modules, it might be recomforting to know that if I just look at the special case where the coefficient C star algebra capital B is just the complex numbers, in that case, an even unbounded Kasparov module is exactly the same thing as an even spectral triple. Just now curly A is the coordinate algebra for this even spectral triple. So it's really a bivariant version of spectral triples that I'm looking at here. And now comes the theorem due to Barge and Schülke. So it has 2 parts. So let's start out with an even unbounded Kasparov module from curly A to capital B. And then the first part tells you how to get a class in KK theory out of your even unbounded Kasparov module. The way you do that is
Sorry, Ali, if you don't. Oh, yeah. Okay.
the thing you do is that you keep the same C star correspondence as you had up here. And then you construct a bounded self-adjoint operator out of your abstract Dirac operator. This bound self-adjoint operator is called the bounded transform of your abstract Dirac operator. It's capital D times 1 plus D squared to the power minus 1/2. And the first part of the theorem of Barge and Schülke says that this pair here is then an example of an even bounded Kasparov module from A to B. And for this reason, you get a class inside a KK theory of A comma B, because whenever you have an even bounded Kasparov module, you can look at the corresponding equivalence class. This is an element inside KK theory. And this is also called the bounded transform of your unbounded Kasparov module. What is perhaps even more important is that the second part here, which says that every class in KK theory is the bounded transform of some even unbounded Kasparov module. So if you look at this bounded transform as a map from unbounded Kasparov modules to KK theory, then this bounded transform is a surjective map. And here it is very important that capital A is separable. But I'm assuming that both capital A and capital B are separable. So,
I have a quick question.
yeah.
Would it make some difference if you, instead of 1 plus D squared to the power minus half, would take 1 plus modulus of D to power minus 1?
It would make a little bit of difference insofar that I don't know that the modulus of D is invertible.
1 plus modulus of D.
Oh, okay, 1 plus modulus of D. I think that works perfectly well.
Okay, okay.
Doesn't matter.
So you want to have some transform which is of like order 0, yes?
Yeah. That is the main point. Yeah. And it's nice to work with this bounded transform. That's a good choice. Yeah. Okay. So now what has happened is that I have argued now that instead of starting out with a bounded Kasparov module, I can instead start out with an unbounded Kasparov module and then try to see whether I can compute the index homomorphism coming from the bounded transform of this unbounded Kasparov module. So now I have introduced unbounded operators into the picture. And so now I'm almost ready to define spectral localizers in this KK theoretic context. I have one extra problem. The extra problem that I'm facing is that if you remember in the very beginning here, I was looking at the spectral projections associated to my abstract Dirac operator, and I was using these spectral projections to cut down this 2 times 2 matrix. But when I work with a self-adjoint and regular unbounded operator defined in the Hilbert C-star modules, these spectral projections, they might not exist. So I have to find a replacement for these spectral projections when I want to define my spectral localizer in this generality. And what I'm going to do is that I'm going to look at what I call a localizing function. Perhaps it has another name, but I think one could call this a localizing function. This is something very soft. This is just a smooth function defined on a real line with values in the closed unit interval. And well, it has to be even, so the graph is symmetric around the y-axis. And then I have 2 conditions. The support has to be contained in the closed interval from -1 to 1. And then actually on the closed interval from -1/2 to 1/2, my function has to be constant equal to 1. And then I have one more condition, namely that my local function, it has to be softly decreasing on the non-negative half line. So if I have inputs x0 and x1, which are non-negative, and x1 is larger than or equal to x0, when I then apply my localizing function, it's going to reverse this inequality. So it's softly decreasing on the non-negative half line. So one could attempt to draw it if one is brave, and I think I will do that. Here. Okay. So here is with lilac. Here's my coordinate system. Here's 1, and out here's -1, and here's 1. Then I have -1/2 and 1/2 here. And so my function has to be constant between -1/2 and 1/2. Then it has to go down so that the support is contained inside this closed interval from -1 to 1. So that's a typical localizing function that we're looking at here. That's the graph of such a localizing function. Okay, so I'm going to...
confused about the condition number 2. How is it possible? It's growing and then it's decreasing. So
it's only when the inputs are non-negative.
So okay.
Only decreasing,
okay.
yeah.
Yeah. Thank you. Of course, yes. Mm-hmm.
So that makes sense. I I hope it makes sense. Okay, so we're going to use this localizing function to construct our replacement of spectral projections in this Hilbert C-star module context we're working in. Okay. Okay, that's very annoying.
Wow, thank you for correctly spelling that Pilkowski. I'm impressed.
What? Okay, sorry. Okay, so now we started with such an even unbounded Kasparov module, and I also have a projection P in the game. And this projection P, it belongs to the coordinate algebra curly A. Okay, and I choose one of these localizing functions. What I can then do is that whenever I have a strictly positive number rho, then I can divide my abstract Dirac operator with rho. So I rescale it. And then using continuous functional calculus, I can apply my localizing function to the abstract Dirac operator divided with rho. And so this continuous functional calculus was developed by Vodonovich and Napiorkovsky. I don't know how to
And
pronounce
perfect
it.
pronunciation, yes, I'm impressed. Not only spell it correctly, pronounce it correctly.
Well, okay, thanks a lot. So, okay, I get this operator phi rho using the continuous functional calculus, and because phi only takes values in the closed unit interval, I get that phi rho here is positive. It's actually a positive contraction. And moreover, because capital D here, my abstract Dirac operator, has compact resolvent, and my localizing function has compact support, I also get that capital phi rho here is a compact operator acting on my Hilbert C-star module.
A quick question.
Yeah.
Do you need to assume that this phi is smooth or it continuous would be enough?
Continuous is enough for until now, but
Okay.
later on, I don't need smoothness. It's just to make it easy that I said it was smooth, but I needed to be differentiable and satisfy some extra.
Like C1, for example, yes, continuous.
Yeah, C1. Yeah, actually, you have a condition on the Fourier transform of the derivative.
Okay. Okay. So smooth is more safe choice. Yeah.
Yeah, smooth is a safe choice. Okay. Okay, so I can form these compact operators, positive compact operators, whenever I have strictly positive number rho, and this operator phi rho only depends on the part of the spectrum of the abstract Dirac operator, which is contained in the closed interval from minus rho to rho. Because phi has support contained in the closed interval from -1 to 1. So this phi rho only depends on the part of the spectrum of the abstract Dirac operator contained in this closed interval from minus rho to rho. So in that sense, I'm here localizing in the spectrum of my abstract Dirac operator. And I'm going to use these compact operators to define my spectral localizer. So let's see what it looks like. I need to have some. Go away. Okay, so okay, I fix my parameters kappa and rho, and then I define this spectral localizer. It looks pretty ugly, and I think in order to understand it, you have to compare with the definition of the spectral localizer in the Hilbert space setting. So I have the definition of that spectral localizer on the next slide. If I can go there. Okay, so here was the old spectral localizer in the Hilbert space setting. So what you see here on the anti-diagonal, you have kappa times the abstract Dirac operator. So if you go back, here you have kappa times the abstract Dirac operator in the second term. Moreover, you have on the diagonal here, you have 2p minus 1 and 1 minus 2p. In this case here, the grading operator is the diagonal matrix with 1 and minus 1 on the diagonal. So what I have here on the diagonal is really just the grading operator gamma times 2p minus 1. So if you go back, you see here gamma times 2p minus 1. So exactly the same thing as for the spectral localizer in the Hilbert space setting. But in the Hilbert space setting, I'm cutting down by the spectral projection Q rho. Now, for C-star modules, I do not have the spectral projection Q rho, so instead I use my localizing function. And I cut down here with phi rho, that is my replacement for the spectral projection. And okay, here I cut down with phi 2 rho. So for a slightly larger index here. And then there's a correction term in the end, which is also there because I'm using localizing functions instead of spectral projections. It is given by minus the square root of 1 minus capital phi 2 rho to the fourth times the grading operator gamma. So this is the spectral localizer in the case of an unbounded Kasparov module and a projection P belonging to the coordinate algebra. The first main result of this talk is that yes, once kappa is small enough, rho is large enough, verify that this spectral localizer is an invertible self-adjoint operator acting on my Hilbert C-star module. If I compute the modulo compact operators, it actually agrees with minus the grading operator. So let's maybe see why this is the case. So let's go back and see if I compute modulo compact operators, this spectral localizer should agree with minus the grading operator. So if I compute the modulo compact operators, well, phi rho is compact. So then this term is 0. And phi 2 rho is also compact. So this term is also 0. But the last term here, phi 2 rho is 0 modulo compact operator. So what I have here is just minus the grading operator. So you see here that the modulo compact operators, the spectral localizer is equal to minus the grading operator. And let me say again, the spectral localizer only depends on the part of the spectrum of the abstract Dirac operator, which is contained in, okay, not the closed interval from minus rho to rho, but the closed interval from minus 2 rho to 2 rho. That's a slightly larger closed interval. So I'm really localizing in the spectrum here. So you have this invertible operator on your Hilbert C-star module. It's self-adjoint and it agrees with minus gamma modulo the compact operators. This means that you get a class in relative K-theory. You get a class in the relative K group coming from the ideal of compact operators sitting inside the bounded adjointable operators. So you get this class in relative K-theory out of your spectral localizer. And in fact, it can be verified that this class in K-theory is independent of the choices that you made. So it doesn't depend on kappa, doesn't depend on rho, and it doesn't depend on my choice of localizing function, little phi. So it only depends on the projection P and my unbounded Kasparov module that I started out with. So this is the spectral localizer class. I'm now going to state what is really the main theorem of this talk. So I want to use the spectral localizers to compute. Are there any questions?
Yes, Jens, it's again Ludwig. Yes. So it doesn't depend on kappa, doesn't depend on rho.
Mm-hmm.
Completely, you could take absolutely small and a large, small kappa, large rho.
Yeah.
Okay. Or just the opposite. I mean, not so large rho and small kappa.
Yes. But
Okay, thanks.
I can only work with kappa and rho such that my spectral localizer is invertible.
Okay, thanks.
Okay, so I want to state the main theorem of this talk, which is that I can use these spectral localizers to compute the index homomorphism. So I have my unbounded Kasparov module. I can take the bounded transform, and I get a class in KK theory of A comma B. This class in KK theory gives you a homomorphism between K groups. It's a homomorphism from the K theory of A to the K theory of B. And I want to compute this homomorphism using my spectral localizers. So my index homomorphism takes values in the K theory of the coefficient C star algebra capital B, but this spectral localizer class lives in this relative K group. So I need to translate from this relative K group, and I need to get a class inside the K theory of the coefficient C star algebra B. So I'm apologizing for the next slide because it's slightly technical, but it explains how you pass from this relative K group to the K theory of the coefficient C star algebra B. How do you do that? So the first thing you do is that you use the stabilization theorem by Kasparov to choose a bounded adjoint isometry defined on your Hilbert C star module with values in the standard module over the coefficient C star algebra B. So here you use that Hilbert C star module is countably generated. So Kasparov's stabilization theorem says that your Hilbert C star module is a direct summand inside the standard module. So this is why I have this bounded adjointable isometry with values in the standard module. The second thing you do is that you realize that this isometry here, it is going to induce a star homomorphism with my isometry. So I get a star homomorphism from the bounded adjointable operators on X with the values in the bounded adjointable operators on my standard module. Just conjugate with V. Okay, it's not going to be unital in general because when I apply this star homomorphism to the unit, I get the projection VV star. And VV star, the image of this projection is isomorphic to my Hilbert C star module X. So VV star can be different from the unit. This star homomorphism is going to preserve the ideals of compact operators. So it's going to induce a homomorphism at the level of relative K theory. Okay, I know, actually I can compute the relative K theory of the ideal of compact operators on the standard module inside the bounded adjointable operators on the standard module, because I can use excision in K theory. So this relative K group is just isomorphic to the K theory of the compact operators. And the K theory of the compact operators, by stability of K theory, it is isomorphic to the K theory of the coefficient C star algebra, capital B. So here I'm using excision and stability to compute this relative K group in the case of the standard module. And here you see the homomorphism that I'm interested in. So I can now use functoriality of relative K-theory to get a homomorphism from the relative K group coming from the ideal of compact operators on my Hilbert C-star module X to the K-theory of the coefficient C-star algebra B. This is how I'm going to translate from my relative K group to the K-theory of the coefficient C-star algebra. I'm doing it in this fashion. And now comes the main theorem. Okay, so let's see. Okay, I have my even unbounded Kasparov module, and I have my projection inside the coordinate algebra. So out of this data, I get my spectral localizer class, which sits in the relative K group coming from the compact operators on the C-star module X. I know how to translate from this relative K group down to the coefficient C-star algebra B. So the left-hand side, and it belongs to the K-theory of the coefficient C-star algebra, capital B. So so that's the spectral localizer part. The right-hand side, let's see. Here I have I have my unbounded Kasparov module, and then I apply the bounded transform. So when I do that, I get this bounded transform here. It belongs to the KK theory of A comma B. Okay, very good. This bounded transform, I get then my index homomorphism from the K theory of A to the K theory of B. So I can apply this index homomorphism to the class in K theory coming from my projection P. So now the right-hand side here is the result of applying the index homomorphism to my projection, to the class in K theory coming from my projection P. And this result of applying the index homomorphism to my projection P actually agrees with the class I get from the spectral localizer. So in this fashion, I have computed the index homomorphism in terms of spectral localizers. And okay, I have a few more comments about this, also relating to the comment by Adam. So I don't know why it's doing that. Okay.
Yeah, it's not really visible, but
it's not visible.
Yeah, I mean, if you write blue on blue, it's hardly visible, but
okay, but
it was clear what you were saying. Yeah,
I to erase it. Okay, so I get from this, I have this index homomorphism that I have been computing using spectral localizers. But you could argue that, well, I was only looking at a projection belonging to the coordinate algebra for my unbounded Kasparov module. But you can use standard techniques relating to spectral invariance and being closed under holomorphic functional calculus to boost this result so that you really get a computation of the whole index homomorphism coming from the even unbounded Kasparov module in terms of spectral localizers. So that is first remark. Second remark is I could, since every class in KK theory comes from an unbounded Kasparov module because of the result of Barsch and Schülke, what I've done here is actually I've computed the entire map from the KK theory of A comma B to endomorphisms of K groups. I've computed this entire map in terms of spectral localizers. So that was what I set out to do and has been done. So I have nothing more to say in this part of the talk. I don't know how much time I have left.
Well, you have 26 minutes.
Okay, excellent. Because
I have
wanted
one
now.
question, if I may.
Yeah, go ahead.
Could you tell me where the multiplication by 1/2 disappeared? Because when you brought the classical result at the very beginning, Adam even asked, how do we know that the spectral localizer is even, and the role of the multiplication by the role of the division by 2 was clearly exposed in the formula, while here I don't know which term has consumed this multiplication if I reduced it to the classical case.
That's a very good question, and it's because I'm cheating you ever so slightly. It's because so it's hidden inside this result here. It's because I'm actually using a different of relative K theory than the one you might be used to seeing, because these two elements I have in here, or this pair, is given by self-adjoint invertible operators instead of a pair of projections, as you would usually expect if you look at relative K theory. So once you translate this and you look at the case where the coefficient C star algebra is just the complex numbers, you really see this half signature appearing once you compute the isomorphism between this K group and the integers.
Okay, so that's why you told Adam at the beginning that it's tricky to see why it's even, and it's hidden exactly here in this isomorphism.
Exactly there. It's hidden exactly there. It's hidden in this isomorphism. And it's because I'm using a different picture of relative K theory. And when you translate things back to the normal picture and take traces, and you see this half popping up.
Thank you very much.
I have a similar one about the parameter, not 1/2, but K and rho. So how you recover the original K theory result when you have to take sufficiently large rho, sufficiently small kappa? In your class, you had no dependence on kappa and rho. So
I have dependence on kappa and rho because I need to know that my spectral localizer is invertible. And you can quantify what that means in terms of kappa and rho.
Okay.
But I only have a spectral localizer class once kappa and rho satisfies that my spectral localizer is invertible.
Okay, I see. Okay, perfect. Thanks. Okay.
I was going to theory on the proof because I wanted to show you why the spectral localizer class is invertible, because that is a really key part of this theorem to verify for which kappa and rho do you get that this spectral localizer is invertible. So I wanted to show you that. But I don't know, I have some problems with Zoom. So I think
Now we're no longer sharing.
I'll need to stop sharing and then share something else instead.
Okay.
I hope that is okay with you. Because it doesn't work when I'm in full screen. Sharing, but I'm going to do that again. Jesus Christ. Can you see this now?
We see Jens Kurt has started screen sharing. Okay, now we see it, yes.
Okay, good. Because now I can annotate on the slides. It was what I planned to do.
Mm-hmm.
So this is about checking that this spectral localizer is actually invertible. So here is, you start out with a key estimate. So you have this localizing function, and what you want to, and you have your projection, which belongs to the coordinate algebra. And what you can verify is that you can find a constant C phi, which only depends on phi. It only depends on phi, on your localizing function, such that when I try to compute the commutator between phi rho squared and my projection P, I can estimate the norm of this commutator. What I get here is the operator norm is always less than my constant C phi divided by rho times the operator norm of the quantum derivative of P with respect to the abstract Dirac operator. This estimate is true for all parameters rho, which is strictly greater than 0. This is a key estimate that I'm going to use when I check that the spectral localizer is invertible. The next thing you do is that you try to compute the square of the spectral localizer. So we look at the square of the spectral localizer. So let's see what happens. So this is also a reminder on the definition of this spectral localizer. So you had, you were compressing with phi rho. What you were compressing was the grading operator times 2p minus 1. That was the first term. The second term was the abstract Dirac operator rescaled with kappa compressed with phi 2 rho. And then you had another correction term, which was minus 1 minus phi 2 rho to the fourth square root of that times the grading operator. So all of this we have to square, and then we are going to see what happens. So first of all, I'm going to square each of these three terms. So when I do that, when I square the first term, I get phi rho gamma 2p minus 1 phi rho squared gamma 2p minus 1 phi rho. That is the square of the first term. When I square the second term, this is not so hard to do because capital phi is constructed using the functional calculus coming from the abstract Dirac operator D. So capital D commutes with phi 2 rho. So the second term I get is just kappa squared D squared times phi 2 rho to the fourth. And the last term is also easy to square because phi, the localizing function, was even. So phi 2 rho commutes with gamma. So the last term I can also square. I just get 1 minus phi 2 rho to the fourth. So that's the square of each of the three terms. And then I have cross terms. So let's see. First, I have cross term coming from term 1 and 3. But because of the way I chose the localizing function, I have that phi rho times phi 2 rho is actually equal to phi rho. This is because the localizing function has support between -1 and 1, and it's equal to 1 on the interval from -1/2 to 1/2. And the same thing happens from the other side, of course. So I have these two identities. So when I look at phi rho times 1 minus phi 2 rho to the fourth, this is going to be trivial. So the cross term coming from term 1 and 3, it's just 0, both of the cross terms. Okay, then I have cross terms coming from term 2 and 3. But capital D anti-commutes with the grading operator, and all the other terms, they commute with one another. So the two cross terms I get from term 2 and 3, they're going to cancel out. It's going to be 0. So I only have cross terms coming from term 1 and 2. And so let me write down these two cross terms. So I have to multiply the first term here with the second term. Remember this relation down here when you do that. So I get plus phi rho gamma 2p minus 1, and then actually kappa d phi rho. Because phi rho, I can commute that past the abstract Dirac operator. That was one of them. That's this term times that one, and I have to do it the other way around. So I get, again, phi rho kappa d gamma 2p minus 1 phi rho. Okay, this is going pretty well, I think. Maybe let's look at the first term up here. So actually, gamma commutes both with p and phi rho. So these two gammas, I can just forget about them. They're going to cancel out because gamma squared is the unit. So, and 2p minus 1 squared is also the unit. So I would really like to move 2p minus 1 past phi rho squared. So let's try to do that. So first I'm going to write down the leading terms. So when I move 2p minus 1 past phi rho squared, 2p minus 1 and 2p minus 1, they're going to cancel out. And I'm just left with phi rho to the fourth. And then I have these two extra leading terms. Plus kappa squared, d squared, phi 2 rho to the fourth, plus 1 minus phi 2 rho to the fourth. Then I have to remember that I took a commutator. So let's add that down here. So I have phi rho times 2p minus 1. Then I have the commutator between phi rho squared and 2p minus 1. And then I multiply with phi rho from the right. Now I have taken care of the whole first term, and I have taken care of these two terms as well. Then I have this error term down here, but you see that on one side, d is to the left of gamma. On the other side, d is to the right of gamma. And d anti-commutes with gamma. So I can put these two terms together and get just a quantum derivative of p. So this is the third term, is these two terms together. So I have phi rho. I remember my kappa. Then I get a quantum derivative times gamma, and then I have phi rho. Okay, so that is what happens when I take the square of this spectral localizer. And I'm now going to divide this square into two pieces, because the first piece here, I'm going to call that T rho. And T rho, that's kind of the leading term. This is, I'm going to check that this is positive and invertible. And invertible. That's T rho. Then I have another term here, which is kind of an error term. E row. That's the sum of the two last terms here. This is going to be numerically small. So we're now going to see what I mean by these two things I put in quotes. So let's first talk about the error term being numerically small. So let's see what happens. So we look at E row is numerically small. What do I mean by that? Let's see. That's some of the two last terms here. I have 5 row on both sides here, and I have 5 row on both sides here. So I'm going to estimate the sum of what I have on the interior here with the interior here. Let's see what I can estimate the operator norm of this sum, which is in between the 5 rows. So I'm going to look at the operator norm of 2p minus 1 times commutator between 5 rows squared with 2p minus 1. Oops. I hate this. Okay, good. I'm back. Plus, that was the interior for the first term in E row. Now I have the interior for the second term in E row. That's this 2 kappa quantum derivative of p times gamma. It's down here. To have plus 2 kappa quantum derivative of p times gamma. And I want to estimate the operator norm of this sum. Okay, I use triangle inequality, and I use the 2p minus 1 is self-adjoint unitary. So I just get operator norm of the commutator plus the operator norm, what I'm left with here, that's just 2 kappa times the operator norm of the quantum derivative of p. Now, this term over here, we can actually rewrite. We can take just 2 outside. Let me do that. So I have here, oh shit. So here we have p inside, I can take 2 outside. And then what I'm left with here, I have an estimate on this operator norm. That is the key estimate that I started out with. That's right here. That's an estimate on the operator norm of this commutator. It's always less than my constant C phi divided by rho times my quantum derivative. That was the key estimate. So all in all, I get here twice C phi, my constant, divided by rho plus kappa times the operator norm of the quantum derivative of my projection P. So I'm going to call this constant here C kappa rho. This depends on both kappa and rho. And for this reason here, because E rho was really given by this sum, and I had 5 rho on both sides, I get an estimate on E rho. So E rho here is less than or equal to C kappa rho times 5 rho squared, and it's also greater than or equal to minus C kappa rho times 5 rho squared. So that takes care of the error term E rho. Then I said that G rho was, so that's a leading term here, G rho was positive and invertible. I'm going to find a lower bound on G rho. So here's a lower bound on G rho. So actually, I'm only going to look at the second term here in G rho. That's the one that involves the square of the abstract Dirac operator. So let's look at d squared times phi 2 rho to the fourth. Okay, it's always larger than what I get if I subtract something positive. So it's always larger than d squared times phi 2 rho to the fourth minus phi rho to the fourth. And this quantity here is always greater than or equal to my parameter rho divided by 2 squared times my operator here. Phi 2 rho to the fourth minus phi rho to the fourth. Why is this true? It's because this function here, phi of x divided by 2 rho to the fourth minus phi of x divided by rho to the fourth. This function here is always going to be positive because of the way I chose my localizing function. And moreover, this difference here is going to vanish. It vanishes on the closed interval from minus rho half to rho half. Again, because of properties of my localizing function. And this function here is what I apply to my abstract Dirac operators to get this difference. When I multiply that with the abstract Dirac operator squared, since my function vanishes on this closed and bounded interval, I'm going to get this estimate. So I can replace the abstract Dirac operator squared by rho divided by 2 squared and get this bound from below. So what I can conclude is that I have a lower bound on the leading term t rho. So the leading term I'm going to keep both of these terms as they were before. I get phi rho to the fourth. And okay, then I have my estimate on the second term. I have to multiply with kappa squared. So I get kappa rho divided by 2 squared times phi 2 rho to the fourth minus phi rho to the fourth. And then my remaining term was 1 minus phi 2 rho to the fourth. Okay, so that's my lower bound on G rho. So I can combine these two things and get a lower bound on the square of the spectral localizer. So now we get a lower bound on square of the spectral localizer. So we get that the square of the spectral localizer, that is what I computed for you. Right here, it's just the sum of G rho and E rho. That was what we saw. So I get that this is the sum of G rho and E rho. And we now have a lower bound for G rho and we have a lower bound for E rho. So I also get a lower bound for the sum of these two. So here was my lower bound on G rho. I'm going to plug that in. So we get this is greater than or equal to phi rho to the fourth plus kappa rho divided by 2 squared times phi 2 rho to the fourth minus 5 rho to the fourth plus 1 minus phi 2 rho to the fourth. That was the lower bound for the leading term G rho. And I also have a lower bound on the error term. The error term was greater than or equal to phi rho squared minus c kappa rho. So I get minus c kappa rho times phi rho squared. And now one can check that phi 2 rho to the fourth minus phi rho squared. This is actually positive. So up here, I can in my estimate, I could as well have written phi 2 rho to the fourth. I still get a lower bound.
Right.
So we're going to write that instead. We have phi 2 rho to the fourth. And now I can start to put things together. Namely, this is actually equal to
Just a friendly reminder, your time is up.
Yes. Okay, thanks. I have one more line.
Sure, take it easy, just,
Thanks a lot. So I get 1 minus c kappa rho times 5 rho to the fourth plus kappa rho divided by 2 squared minus c kappa rho times this difference. Then I have to add 1 minus phi 2 rho to the fourth. So what you see now is that if this constant c kappa rho is strictly less than 1, then this term here is strictly positive. This constant is strictly positive. And if c kappa rho is strictly less than kappa rho divided by 2 squared, then this coefficient here is also positive. Okay, this is bad. So if this constant here is strictly less than 1 and strictly less than kappa rho divided by 2 squared, then both of these coefficients are going to be strictly positive. And in this case, I get that this whole estimate from below becomes strictly positive. Then there exists delta strictly greater than 0, such that L kappa rho squared is strictly greater than equal to delta, which is then strictly greater than 0. So in this case, once I arrange to have these two strict inequalities, I get that the spectral localizer is invertible because the square is greater than or equal to a strictly positive constant. Thus, L kappa rho is invertible. And because c kappa rho, because of the nature of this constant, you can see that you can choose kappa and rho such that these strict inequalities are satisfied. So that's why that the spectral localizer is invertible once I choose kappa and rho appropriately. I think I have nothing more to say, but if you have questions, especially to the last part here, then don't hesitate to ask.
Okay, so let us thank Jens for his beautiful talk. Thank you. Okay, anybody any questions? Anything in the room? No? Dimitri?
Thanks for the very nice talk, Jens. Okay, so you got a question before, like about how computable is the classical setting, the K-homology. But do you think that there is a chance in your setting to do computations?
That depends on what you mean by computations. So I think it is valuable that this spectral localizer really only depends on a part of the spectrum of the abstract Dirac operator, which is contained in the closed and bounded interval, because often you don't have access to the full spectrum of the abstract Dirac operator. So in that sense, I think it could be very useful.
Yeah, go ahead, Tom. I have a question. Do you have some efficient way of estimating this biggest kappa and the smallest rho?
Yes. So
where it is stable range?
Yeah. So this is something that you can indeed do. I mean, so if you permit me to just, so I have this, my C kappa rho has to satisfy these two strict inequalities, and I didn't do that in the main part of my talk. But if you look at the definition of C kappa rho, so let's maybe do that.
Can you use instead of C kappa rho some other norms? I don't know.
You have to use
something related.
Also, this is the same thing that appears in the work of Terry Loring and Hermann Schulz-Baldes. So this C kappa rho, what you see here is it relates to the operator norm of the quantum derivative of my projection P. And otherwise, C phi here, this is an explicit constant that you can compute in practice. It only depends on your choice of localizing function. So once I choose kappa, such that 2 times kappa times the norm of this quantum derivative is strictly less than 1, then I can easily find a rho afterwards such that my 2 strict inequalities are satisfied.
Okay.
So I have an upper bound on what kappa can be, because C kappa rho has to be strictly less than 1.
Thank you.
I have one more question. So is it conceptually possible to obtain something similar, like to generalize it even further to the general Kasparov product?
I have
instead of taking a product with. Sorry, I couldn't hear you.
What?
I couldn't hear you. You were saying something.
Okay. That was because I was. I think it's that the reason why I have any chance of computing the Kasparov product in this fashion is because I have an explicit formula for this index homomorphism. Because it's just so this index homomorphism coming from my unbounded Kasparov module, it's given by when I apply it, which belongs to my quantity algebra. It's really still just given by compressing the abstract Dirac operator by P. This gives me an unbounded Kasparov module from the complex numbers to B. And because I have this explicit formula for the index homomorphism, that's why I have any chance of computing it. In the general case, I don't have a very explicit formula for the unbounded Kasparov product.
Yeah, it confused my question because basically this index homomorphism is computing the Kasparov.
Yeah, but I'm saying like more general instead of having K-theory groups to have more.
Okay, not just K-theory. Okay.
Yeah.
Okay.
But more work needs to be done so that you get to there. This is what I understand. Yes.
Okay.
Thanks.
I think that would be a very hard problem, and I don't. I have to be careful what I say, but I don't expect that you would get a sensible formula out of it in general.
Okay, anybody else? Adam?
Yes. May I have a question? I have a maybe slightly conceptual question. Since spectral triples are a main object of interest in non-commutative geometry, and in this philosophy of non-commutative geometry, one thinks about spectral triples like a non-commutative version of manifolds. But on the other hand, you mentioned that these unbounded KK modules are like morphisms generalized between sister algebras. So I don't know, how do you view it? That this is some general form of non-commutative manifold, even enhanced in some way, or?
I typically think of an unbounded Kasparov module as what you get if you have a fiber bundle and you have like a vertical Dirac operator. So if you have a fiber bundle and you have a vertical Dirac operator, this gives you an unbounded Kasparov module, which links the total space of your fiber bundle to the base space. So kind of unbounded Kasparov modules, that's the general version of vertical Dirac operators. That's a nice, vertical Dirac operators gives you a nice class of examples of unbounded Kasparov modules that arise naturally from some geometric input.
Do you think about this unbounded KK module as some notion of generalized morphism between, I don't know, between maybe spectral triples? Or?
Yes, but maybe, so that, we have been spending a long time thinking about unbounded Kasparov modules as perhaps giving you morphisms between spectral triples. And this sometimes work, and there's by now quite a lot of work available on this topic related to the unbounded Kasparov product. So you can really use unbounded Kasparov modules to build new spectral triples from existing spectral triples.
But can you arrange it like into a category, like you have a category of sister algebras with morphism being elements of the KK group?
You have a category like that where the objects are C-star algebras and the morphisms are KK groups indeed, and the composition of morphisms is given by the interior Kasparov product. But as I know, there's currently not a version of this for spectral triples and unbounded Kasparov modules, even though I think that many people have been working on this for a while now.
Okay.
Maybe do you have more input on this, Bram? If you're still here.
I have one more question.
Yeah, go ahead.
One more question, in fact, about sorry.
No.
About the second bullet point of this slide. So I guess the whole reason for this is to find a more computable approach to this index problem. But can this approach also say something about the surjectivity of the map from KK-AB to the homomorphisms? Like, could you, from these, since you have more information, or you can leverage more information, say something about the surjectivity, and then get an approach to UCT? Something?
I don't know about that. I was really interested in these spectral localizers because I'm actually hoping to construct homomorphisms of K groups that do not come from classes in KK theory. It's a slightly different question.
The other way. Okay.
But but I haven't thought about whether it gives you insight on the UCT problem. It's, I don't know.
Yeah.
I have one more question, if I could.
Yeah.
So in the context of spectral triples, there is an important notion of being finite summability, the notion of finite summability. And I wonder, okay, in this context of Hilbert modules, you have this notion of generalized compact operators. And how about this generalization of this so-called these Schatten ideals, LP classes? Is there anything of this?
I think currently there's nothing except when the coefficient C star algebra is a billion.
Uh-huh.
So in that case, there's some theory available. But in general, it's a very difficult problem to construct construct a nice version of Schatten ideals for Hilbert C-star modules. Yeah.
Okay, thank you.
Yeah, go ahead. I have a question. So you said something about the applications to physics, for instance. So my question is your localizing idea related somehow to cut off in let's say quantum field theory or something like this, even if it is con approach to the standard model.
Yeah,
Can you see?
It's a bit outside my area of comfort to say something about that. But
So forget about physics. What about Kant's idea of cutoff?
Yeah, so I know very little about that, so I'm maybe not the right person to ask here. I think that, okay, let me say something. So there's this new approach to K-theory using operator systems. And there it's very much motivated by spectral localizers. Because you get what you get is that, okay, maybe go to the beginning. So if you look at this spectral projection, which you get from the abstract Dirac operator, you could use that to localize your information, but you could also localize your coordinate algebra using this spectral projection. So instead of working with curly A, you could cut down your coordinate algebra by multiplying it on both sides with one of these spectral projections. If you do that, you get an operator system. And it's a very good question how much of the K-theory of the C-star algebra can you see by only looking at these operator systems? Yeah. And
so these operator systems, they ignore this infrared and ultraviolet parts of the spectrum. In a sense. Okay.
That could be the case. Yeah. I'm really not trained in physics. I would rather not say anything that is incorrect there.
Okay.
But sorry, this K theory in this context of operator systems is straightforward to define, or?
No, it's not. So there are some papers by Walter van Zeulenkamp where he's defining K theory of operator systems, but it's very, very recent work. So it's still a theory that has to be understood much better.
Okay.
He's talking a couple of weeks, but I haven't read his abstract yet, so I cannot confirm that it's this topic. But Walter gives a talk in a couple of weeks.
But very stupid question. You don't have projections, yes, in these operator systems.
No.
Okay. So you somehow need to proceed in different manner, yes?
Yeah.
Huh.
That's right. Because an operator system, you haven't got any algebra structure, so it doesn't really a priori makes much sense to talk about invertibles and projections.
Oh, so this is remarkable that you can define K-theory. Wow.
Yeah, it is really interesting. And so if you have, if you have a spectral triple, you have lots of these operator systems because you can choose any positive parameter rho, and then you can truncate your quantity algebra by this spectral projection. You could kind of hope that they converge in some sense to the K-theory of the whole quantity algebra. But this is speculative. No one knows, I think.
Okie dokie. Any further questions going once? Any further questions from the Zoom, perhaps? I don't know. Ali, whoever else? No?
Maybe one last question. You mentioned that there is a problem in defining these ideas, this generalization of the Schatten ideas, but still there is a notion of being, for a spectral triple, for being theta summable. This is slightly weaker.
Yeah.
And maybe there is some notion of the generalization of this theta summability in this context of Hilbert model, or even this is problematic.
That is, I think it is really a very difficult question to answer properly. Because you don't, even say you don't know what Hilbert-Schmidt operators is, and you don't know what trace class operators is. Even these two things are missing.
Okay, I see. If you have problem with trace class, then you have problem with theta summability. Since I thought that maybe it is hard to define every LP, this whole family, but maybe trace class would be somehow easier.
That would be nice if you could define trace class operators in a good way. Yeah, I have actually been thinking about this quite a lot without success, also together with Bram Mesland, but we couldn't figure out how to do it. So, in the case where the C-star algebra B is commutative, then yes, but that's maybe not the most interesting setting. Yeah.
Okay, I think it's really time to wrap it up. So let me ask my two quick questions. One, could you point into some particular application where you would really use your generalization? It's always nice when you generalize somebody's theory that you show an example that goes beyond the former theory, but concrete example. And the second one, if it's not taking too long, could you just slightly elaborate on this weird relative K theory that you used in your talk? Just
if I could only remember how I introduced it. That is the main problem. But the classes are kind of differences of invertible operators. Self-adjoint invertible operators instead of pairs of projections.
And how do you translate between one and another?
It's because if you have a projection P, then you get a self-adjoint unitary operator, which is 2P minus 1.
This way. Okay.
That's almost
okay.
It's not.
Okay. I'm happy. And now the other question about some hint at a possible interesting example.
Yes, I have. Okay, I have my own secret reasons for doing this. So I have a very interesting setting that I'm interested in here. Yeah. but I haven't finished it yet.
Okay. So that's still classified. It's still classified work.
It's it is kind of classified. But it is. I'm really interested in this because I would like to have another way of constructing homomorphism between K groups. So I really want to find something which is not necessarily a class in KK theory, but which gives you homomorphisms between K groups. Yeah.
Sorry, may I have one last question? Forgive
If you
me,
must.
Piotr, forgive me. In this context of this generalized unbounded KK modules, in this context of Hilbert modules, Dirac operator encodes much information about the underlying geometry, about the dimension, about the volume of the underlying manifold, and so on. And how about this, for example, growth of this spectrum of this Dirac in this generalized context? Do you see some geometric properties or?
It's the same. I mean, the problem with this general theory is it's related to. I mean, if you want to talk about growth of eigenvalues, for example, I mean, there's no notion of Scherden ideals in this context. So, what you really use unbounded Kasparov modules, what you use them for the time being, is that you use them to construct new spectral triples from existing ones. That is the main application, I think. Okay. I don't know whether. So the idea is that. Okay, so. Okay. If you have one of these even unbounded Kasparov modules from A to B, then suppose that you have a spectral triple over B. Okay, and then you might like to construct a spectral triple over A instead. And the way you can do that, if you both have a spectral triple over B, and you have such an even unbounded Kasparov module, then you can try to construct what is called the unbounded Kasparov product. And this is a method that allows you to construct candidates for spectral triples from curly A out of spectral triples over capital B. So there's some recipe that you can use that allows you to use unbounded Kasparov modules to construct new spectral triples out of old ones. And this recipe is called the unbounded Kasparov product. And it really recovers, when you pass the bounded level, you recover the interior Kasparov product out of this recipe.
Okay, so once again, we would we don't think about this unbounded Kasparov module as a geometric object, but rather a way of turning one geometric object into another. And we are interested in geometric properties of these algebras A and B, corresponding manifolds, like for example.
Yeah. So.
Wait, so in particular, in the commutative case, would you find the way of turning one smooth manifold to another smooth manifold?
Well, I don't know, but you can. I mean, if you were in the case of a bundle.
Well, these are commutative spectral triples.
Yeah, but it's still much more than the naked manifold.
Okay, so manifold with extra structure, yes, fine. But in particular, you have a manifold.
Yeah, so we have computed this unbounded Kasparov product in the case of fiber bundles, for example. And what you get is that if you start out with a Dirac operator on the base, and you have some vertical Dirac operator, you can take this unbounded Kasparov product and you get a Dirac operator on the total space, which agrees with the Dirac operator you would get from the spin structure on the total space up to some curvature term. So you can really, I mean, you can play with this a lot, but it's maybe more interesting to do it in the setting where you have spectral triples on the coefficient C-star algebras, but you don't have any spectral triples on the quantity algebra curly A. So there are many examples of this situation. And in this case, this unbounded Kasparov product really gives you a method of putting the pieces that you have together. So spectral triple over B and an unbounded Kasparov product, you can put them together and get new exciting spectral triples on curly A. And this then covers what happens in classical situations coming from fiber bundles, for example. Yeah.
Okay, I'm happy.
Thank you.
Let us thank Jens again. Thank you so much, Jens.
Thanks for listening and inviting me.
I stopped recording.